Okay, I'm going to explain the whole of electromagnetism in one video. Here we go. Right, our starting point is this. If you send a current through a wire, I is the symbol for a current, then it will produce a magnetic field. Okay? A current carrying wire always produces a magnetic field. So, to work out what the magnetic field looks like, you use your right hand, curl the fingers over, stick your thumb out like so, and point your thumb in the direction of the current. And the curl of the fingers tells you the direction of the magnetic field. It forms a circular pattern around the wire. Okay, so right hand, it's going to curl around the wire like this, which means it's going to try and draw it in 3D. It's going to look something like that. Okay, so that means that arrow there, it's going down on that side of the glass, closer to you guys. Okay, and it's coming up here on this side of the glass, closer to me. Okay, so that's what the magnetic field looks like, and a current always produces a magnetic field. You might not have been told that before now, but it does. Okay, so we can use this fact to do some clever stuff. So let's see what happens when we take a wire and bend it into a coil. So we'll send in some current here, so it flows in this direction round the coil and back out. Okay, and we're going to use the right hand rule to work out what the magnetic field looks like around that coil. Right, I'm going to be using these two symbols to represent magnetic field going out of the glass towards you or into the glass towards me. If it's going out of the glass towards you, it looks like that. If it's coming into the glass towards me, I'm going to draw it like that. This is common notation. If you haven't seen it before, then you need to remember it because it might come up in your exam. Okay, so right hand, let's look at the current here. It's going in that direction, which means the magnetic field is curling around like that. So that means it's coming towards me in this region here. Okay? And it's going towards you on this side of the wire. That's that bit of current there, because the current's flowing in that direction. Right hand. Okay? Let's do this bit. Should be the opposite, right? Right hand, current in that direction, so it's going towards you in this region here. Okay? So towards you is that, and then coming towards me in this region here. Okay? So yeah, above the wire, it is the opposite. And below the wire, it's the opposite, because the current is in the opposite direction. That's what you'd expect. And already, can you see what's happening? Inside the coil, the direction of the magnetic field is towards you. And I bet you we get that again if we look at this bit here. So, right hand, current in that direction. So, magnetic field is going towards you in this region here. Yep. And it's coming towards me here. Finally, this side, current is It's going up there, so it's curling towards you here and back towards me here. And so, using the fact that a current carrying wire always produces a magnetic field, we can create a region in which the magnetic field is pointing in the same direction inside a coil. So we can take that one step further and put many coils together, all with one wire, and make what's called a solenoid. So we send current in here and back out there. Okay, so the idea here is we've coiled this one wire in this pattern, so if you look down from the top it would look like that, right? So I've tried to draw it so this bit here looks closer to you and this bit is closer to me. Yeah, okay, so the current there will have that bit closer to you and comes round, and this bit here, when the current's going in that direction, is closer to me. Okay, because that would match up with this if we're looking at it from above. The bit's closer to you, current's going in that direction. Bit that's closer to me, current's going in that direction. Okay, good. So that means, using the right hand rule again, we can work out what the magnetic field is going to be around this solenoid. So here, okay, it's going up on the outside closest to you, and it's going down on the inside of the solenoid. Okay, so it's going up closest to you, down closest to me. Okay, so that matches up with that bit there. And then when the current has come round and the bit that's closest to me here, it's in that direction, so it's curling, it's going down on the inside of the solenoid and coming up on the outside nearest to me. So again, it does match that. So it's coming up nearest to me and down on the inside. Okay? And this bit here, where the current is flowing sort of away from me towards you, that's that bit there, same thing. It produces magnetic field, curls around like that, so it's going down on the inside, okay, and up on the outside. And the same here, where the current is coming towards me, down on the inside and up on the outside. It looks more like it's going down there. It's meant to be 3D. It's meant to be, that looks a bit better there. I'll just leave that one. Anyway, I'm sure you've seen the point of all this by now. All of these, for each individual loop, they're all the same. So they all behave like this and they all add up. Each individual loop produces a magnetic field that goes down like this. So when you add up all these individual loops, you get one big magnetic field going down the middle. So you get that one big magnetic field line going down the middle. Okay, In fact, the whole of the interior region just like here, the whole of the region inside the solenoid, all the magnetic field is pointing down. It all adds up. They all conspire to produce one big magnetic field like that. And likewise, on the outside of the coil, it's all going up. So in this region, all the individual bits that add up, it just produces one big magnetic field, all pointing upwards. And does this pattern look familiar? That's right. It's exactly the same pattern as a bar magnet. So these two will join up outside the solenoid. Okay. And it's the classic butterfly pattern of a bar magnet. So you can have some more lines here. Okay. Like so. Magnetic field in this direction. There we go. So, just from using the simple fact, well, it's quite a deep fact really, it's how the universe has been made, or is, that a current in a wire produces a magnetic field, we can make, by sending a current through a solenoid, a magnet. Well, an electromagnet. It becomes, you can do it. I hesitate because to describe it as an electromagnet, you just need one final thing, and that's you just need to put a soft iron core inside the coil. That just makes it stronger. Okay, so you just put a lump of iron, not a magnet. It doesn't have to be already a magnet, just a non-magnetized iron core, and wrap the solenoid around it, wrap the wire around it, and then you've got an electromagnet. And the pattern is exactly like that, as if it were just a north-south magnet. In this case, north's down there, south's down there. So you've got the, be consistent with the colours. So you've got your classic butterfly pattern, like so. So an ordinary magnet produces exactly the same field lines and pattern as an electromagnet. So that's how you build an electromagnet. You take a wire, you coil it round an iron core, and you send a current into it. And because of this, it turns the whole thing into a massive magnet, an electromagnet. Brilliant. Okay, there we are. I think that's everything I want to say for the first bit. Yes? Oh yeah, one more thing. I knew there was one more thing. When you wrap the wire around the iron core, the wire must be insulated. Okay? If this wire, if you've got your iron core here, okay, and you wrap the wire around it, so a naked exposed metal wire, okay, that ain't going to work because you've got the metal of the wire in direct contact with the metal of the core. So current coming in is going to go in there and it's just going to go straight through the core itself and then back out there. The wire has to be insulated. You know, like the electrical wires in your house, there's a plastic sheath on the outside of the metal, and that's what you have to use. So there can't be any conduction between the wire and the core. Anyway, right, that's that bit done. So, first bit, just remember that any current flowing produces a magnetic field. Great. Right. Okay, so the next bit is this. A current in a magnetic field, a wire carrying a current in a magnetic field experiences a force. So, if you have a magnet like so, okay, the North Pole and the South Pole here, okay, so the ends of two magnets, that will produce a magnetic field in between them, okay? If you place a current carrying wire in that field, right, that wire will feel a force. Okay, now to work out the direction of the force, it's either going to get pushed up or pushed down. Okay, you use your left hand. This is called Fleming's left hand rule, or the motor rule, because it's how this is how motors work. So you take the left hand like so. The first finger is the field. So first finger for the field. In this case, the field, the magnetic field, is in that direction from north to south, right? The second finger is the current. Second for current. So your second finger, the current, so first finger field in that direction, the current is coming from you towards me, so like that. Okay, so in that direction. Right, so, and then your thumb tells you the movement direction. Thumb for movement. Or the force. Movement, force. Direction of movement, direction of force. So, first finger field, current. Right, the thumb, the movement, downwards. So we've worked out that the force that this wire will experience is downwards. Okay, so that's F. So, just remember, if you place a wire that has a current going through it in a magnetic field, it experiences a force. That's just a law of nature, okay? And use Fleming's left-hand rule to work out the direction of the force. So, just like with coils before, we can be clever with this. What if we arrange this wire in the shape of a coil? Let's see what happens. Well, just quickly draw this again. Okay, so same setup. We have a magnetic field going from north to south like that, but this time we're going to have a coil of wire in the magnetic field. Okay? And let's send current in that direction. So it's flowing in that direction there and back in this direction here. Right. Well, as we know, we have current in a magnetic field, so this bit of wire is going to feel a force, and so is this bit. So let's work out the direction for each. Well, this bit here, it's going to be down. We've already worked that out. So let's just draw that in. This stretch of wire here will feel a downwards force, like so. But the current for this bit here is in the opposite direction, so it'll feel a force upwards in the opposite direction to this one. And let's just prove that, let's check it. Left hand, motor rule. First finger field, it's in that direction, it's the field. Second finger current, well, it's going towards you. I've tried to draw it 3D, so from me towards you, so that's like that. And the thumb is the movement upwards. Yes, it's correct. This side will feel a force upwards. And that's why it's called Fleming's left-hand rule is called the motor rule. We've built a motor. That's exactly how a motor works. Because look, if you have a coil of wire with a current flowing around it like this in a magnetic field, one side feels a force down, the other side feels a force up. So it spins like that. And that's a motor spinning. It's how they work. Simple as that, really. Now, you might have guessed that we could run into problems here because this wire, these two wires, the in and the out, are going to get twisted up if this rotates. So there's a little device called a split ring commutator that solves this problem. And what you have is the coil that rotates itself, the wires that come out of it look like that, okay? And you have these two split rings. It's not the greatest drawing in the world, but I'm just trying to show that you've got these two bits of metal like this that are not touching at the top and bottom. There's a gap in between them, okay? And you connect those to the power supply that provides the current. The current's going down there, down that side and back this way, which means that is the positive side. Okay? So this bit here, the end of the wire that's part of the coil, brushes against the ring as it goes by. And then just for a split second as the coil rotates, it's not in contact with anything at the top there in the gap. And then it connects with the other half of the ring. That's how a split ring commutator works, and that's how you arrange it so that current on this side is always going in the same direction, and on this side it's always going in that direction, even though the coil's rotating. Okay, right, I think, yeah, that's all I want to say on the left-hand rule. That's how motors work. Obviously, motors are a huge part of modern society and technology because they're in everything. So this is important stuff. Right. Next bit. Okay, next bit. If you force a wire through a magnetic field, it will generate a current. So, Similar setup to before. You've got a magnet, okay, with magnetic field going from north to south, as usual. Now, we have a wire in that magnetic field. But this time, rather than putting a current into the wire and getting movement out, we're going to put movement into the wire and get current out. So this is a generator. So we're going to force it down, grabbing the wire and pushing it down through the magnetic field so that the wire cuts the magnetic field lines. Okay? Now, to work out the direction of the current, this is a generator, so we use the right hand generator rule. Same as before, only with your right hand instead of your left. So, first finger is the field, from north to south in that direction. The thumb is the movement. Now we're pushing it down, the force down, so the movement is down like that. And therefore the current is going from me to you, out of the glass in that direction. So current is from me to you. I'm laughing because of the Chuckle Brothers. Have you ever seen those guys? You should Google them. Anyway, that's it. That's how generators work. And again, we can be clever. If we make a coil like before, let's see what happens. So, two magnets, north and south, magnetic field. Okay, and the coil will be something like this, just like before. Right, let's send current in, let's push that side down. So the force is down there. We're going to make this thing rotate, so we're pushing that side down and we're pushing the other side up. Okay? So we're putting in a force and we're going to get a current out. It's a rotational force, so that means pushing one side down and the other side up. Now, we know from this diagram, if we push that side down, current will go in that direction, so the current on that side is like so. So therefore, because the force is in the opposite direction here, the current should be towards us. Let's check. Right hand rule, field from north to south. Thumb is movement, it's up like that. So the current from you to me. So yes, it's in that direction. Okay, good. Right. So, just to reiterate, it's a generator, we're putting in movement, we're putting in the rotational force, so we're getting out current, so we're generating current, hence generator. The setup around here is slightly different. Rather than the split ring commutator, you still have this sort of brush system where the wire brushes against the contact, but they're fully circular contacts this time. So it's in permanent contact with these two metal rings, which are separate but fixed, and you connect those two metal rings to whatever you want, just to show that there's a current flowing. It could be a bulb, a lamp which will light up when current's flowing, something like that, or it could be a voltmeter to show a voltage. Anyway, right, so that's the generator. So the next bit, this demonstrates what we call electromagnetic induction, right? when you force a wire through a magnetic field, a current is generated because of the principle of electromagnetic induction. Right, I want to get this right, so I'm going to read it out. Electromagnetic induction is the generation of a potential difference across a conductor which is experiencing a changing magnetic field. Okay, that's the definition. Now, the word changing is crucial. In this case, we're forcing a wire to cut through these magnetic field lines, and it's that cutting that means the magnetic field in that wire is changing. Same thing here. Because this wire is moving down through the magnetic field lines and cutting them, the magnetic field in that part of the wire is changing. Therefore, a potential difference is induced and therefore a current flows. Same for this bit. So the key point is that it's not so much the cutting of the magnetic field lines, it's the fact that the magnetic field is changing. And that means there are other ways we can use the principle of electromagnetic induction to generate a current. For example, let's do some examples. You can have a bar magnet and a coil like that, and connect that to a voltmeter or a bulb or whatever, and you can either keep the magnet still and move the coil up and down past the magnet, or you can keep the coil still and move the magnet. It doesn't matter. In both cases, because the magnet has a big magnetic field all the way around it, okay? If you move that coil, if you move them relative to each other, you can move both if you want. That coil will be constantly cutting these magnetic field lines around it, and therefore it has a changing magnetic field in the coil, and therefore it induces a potential difference in the coil, and therefore it produces a current in the coil. That's the order of events. Okay? So it's the changing magnetic field that matters. But it also means you could have this setup. Okay, you can have a coil here, right? Let's put a resistor in so we don't have a short circuit. And let's add a switch as well. Okay. And then you can have a physically unconnected circuit here with a bulb in, say. Okay. And when you close this switch, current will flow, in that direction. Current will flow in this circuit. Okay, so the current will go from 0 to some number, which means the magnetic field in this coil will go from 0 to something. Okay, so you get a magnetic field in this coil here. And because this coil, even though it's physically unconnected, it's sitting inside the magnetic field of this coil, solenoid, I should say, to be technically correct. That means the magnetic field that this solenoid is experiencing goes from 0 to something. And so it has experienced a changing magnetic field. And therefore, the changing magnetic field induces a potential difference in the coil, and therefore current will flow, and therefore that bulb will light. Okay, so there's more than one way to achieve a changing magnetic field. And finally, the last thing I want to say on this is this last example, the bulb only lights whilst this coil is experiencing a changing magnetic field. Once this has achieved steady state, in other words, once it's been the switch has been closed and current has been running for a few seconds, few minutes, whatever. It's a constant current in there. That means there's a constant magnetic field in this solenoid, okay? Which means this solenoid is sitting in a constant magnetic field. The magnetic field is no longer changing, and therefore the bulb will not light because no current will flow. A potential difference is induced and current only flows when the magnetic field is changing, okay? This solenoid could be sitting in the strongest magnetic field ever, but that bulb will be off as long as that magnetic field is not changing. If it's constant, the bulb is off. So once it's achieved steady state, that bulb is off. Now, if you then open the switch and stop this current flowing, then this magnetic field here in this solenoid, because the current has gone from something to zero, the magnetic field collapses. It goes from whatever it was to zero. And that means this now experiences a changing magnetic field when you switch this one off as well as on. And therefore, the changing magnetic field will induce a potential difference, therefore current, and therefore that bulb will light. But only whilst it's changing. Again, when it achieves steady state and no current's flowing and it's settled down after you've switched it off, there'll be no magnetic field there, no magnetic field there, no changing magnetic field, and no current. Good. Right. Next, transformers. Okay, transformers. So a transformer is a large iron core like this, which has two coils of wire wrapped around it. One on this side, this is called the primary coil, okay? And one on this side, the secondary coil. Okay, and they both have a different number of turns. So, this is the primary coil voltage that we put in, and we get out a certain voltage of the secondary coil. So primary coil, secondary coil. Okay? Now, you also have a certain number of turns, the number of times this coil has been wrapped round the core. And on the primary side, it's the number of turns of the primary coil. On the secondary side, it's the number of turns of the secondary coil. Good. So that's the internal workings of a transformer. Now, how does it actually work? So, what we do, we put in a certain voltage, the primary voltage, and we get out a different voltage. So that's the input, if you like, and that's the output. Firstly, the voltage we put in, it has to be AC, alternating current. Transformers do not work on direct current. And the reason is electromagnetic induction. This current has to be changing to set up a changing magnetic field in this coil. If it's direct current, there's no changing magnetic field and therefore it doesn't work. Common exam question. Anyway, okay, this is the order of events. We put in an alternating current into the primary coil. Okay, so you have an alternating current in the primary coil. So one moment it's going one way, the other moment it's going the other. Okay? Next, that creates an alternating or changing magnetic field inside the primary coil. Okay, next. The iron core holds most of that magnetic field inside it and transfers it to the secondary coil. Next. This means that because that magnetic field is changing all the time, the secondary coil experiences a changing magnetic field. And because of electromagnetic induction, this induces a changing magnetic field in the secondary coil, induces a voltage or potential difference in the secondary coil. And that is Vs. That's the output. And that's it. That's how transformers work. That's the sequence of events. And that, again, is a common exam question. So just describe it exactly like that in that order. Emphasize the changing. Has to be a changing magnetic field. Okay, good. Now, there's an equation that goes with all this. You can work out what the secondary voltage is, or the output voltage, from the number of turns, if you know the ratio of the number of turns. Anyway, the ratio of voltages is the same as the ratio of the number of turns. So, in equation form, that means that the ratio of the primary voltage to the secondary voltage, in other words, the primary voltage divided by the secondary voltage, or voltage in divided by voltage out, is the same as the number of turns in divided by number of turns out. Right? And often they ask you to work out, say, the number of turns on the primary coil, and they give you the primary voltage, the secondary voltage, and the secondary number of turns. So let's just do a quick example. Let's do that. Let's work out number of turns on the primary coil if number of turns on the secondary coil is 1,000, say. Let's say the primary voltage is 100 volts and the secondary voltage is 50 volts. Let's work out number of turns on the primary coil. Well, rearrange that equation, and NP is Vp times Ns all over Vs. So that is Vp is 100, Ns is 1,000, and Vs is 50. Okay, and that turns out to be primaries must be 2,000 turns. Okay, and that's what you'd expect, because like I said, the ratio of voltages is the same as the ratio of turns. So the primary to secondary voltage is 100 to 50, so 2 to 1, and therefore the ratio of NP to Ns must also be 2 to 1. So if Ns is 1,000, that must be twice as big, so NP must be 2,000, and it is. So that would be called a step-down transformer. You're putting in 100 volts and you're getting out 50 volts. To do that, you've got twice as many turns on this coil as that one. A step-up transformer, you have fewer turns on the primary coil and more on the secondary, and that way you can increase the voltage from a smaller to a larger voltage. There you go, that's it. That's the whole of electromagnetism in one, admittedly, pretty long video. Whew.